All right, it's time to look at energy. We already looked at work and power, and so now energy, since this unit is called work, power, and energy. Energy is simply the capacity to do work, right? If someone says, will you take out the garbage? You might say, oh, I don't have the energy. So it's the capacity to do work. In other words, if you're going to do work, you're going to need energy to do it. Now, there's all kinds of various forms of energy. There's mechanical and thermal and nuclear and sound and heat and electrical, okay? The type of energy that we're going to be dealing with is mechanical energy. And under mechanical energy, there are several different types. You've already heard about some of them. Okay, so energy is the capacity to do work. If work is done on or by a system, then that system is going to either gain or lose energy. So the total amount of energy will change. Okay, so when work is done, you might want to write this down. When work is done by or on a system, the total energy of the system will change. When work is done on or by a system, on or by a system, the total energy of the system will change. The total energy of the system will change. Okay? So how does it change? So if one system does work on another, the one doing the work is going to lose energy, and the one having the work done is going to gain energy. One of them loses and one of them gains. Okay? So if work is done by a system, it's going to lose energy as it does it. If I lift a book, me and the book are the system, I'm losing energy as I lift the book, but the system's gaining it. Okay? So when one system can do work on another, we say one system has energy relative to the other, and then the first system loses and the second one gains an equal amount. So one system does work on another. The one doing the work will lose energy, and the one having the work done on it will gain energy. And in the perfect ideal world, the amount that one system loses, the other one will gain. So there's a transfer of energy happening here. And so the work done by one equals the change in energy in the other. And that leads us to something that we're going to use a ton in this unit and the next. Work done equals the change in energy. So if I do work to lift a textbook, we could calculate how much work I did, and that would be equal to the change in energy of the textbook. If I do work pushing a cart across the desk, then the work that I've done will equal to the change of the cart's energy. The type of energy that changes depends on what's going on. So lifting a book, I'm changing its energy with respect to gravity. Pushing something across the desk, that's in motion. I'm giving it kinetic energy. I'm increasing its motion. Okay? So let's look, since I just said those words, let's look at kinetic energy that we met in the momentum unit. Kinetic energy, we said, was energy of motion. And I already gave you the equation. It's capital E with a subscript K, and it's equal to 1/2 mv squared, where m is the mass of the object, v is the velocity of the object, and it's just the v that's squared. And we already did the units too. They were kilogram, meters per second that gets squared. So kilogram meters squared per second squared, which is a kilogram meter per second squared times a meter which is a Newton meter, which is a joule. So energy and work done are both measured in joules. Okay, so this is kinetic energy. And the first questions I'm going to give you in the textbook tonight are really pathetic. They give you the mass, they give you the velocity, they ask you to find the kinetic energy. I know you will be able to do them. Okay, but we set up here work done is equal to the change in energy. So I just want to show you how that's true. So we know work is F delta D cos theta. And assuming that the F and the delta D are going in the same direction, theta then will be 0, and cos theta will be 1. And we know F is equal to MA. So then really work would be equal to MA delta D, subbing in for the F. But we know A is equal to VF minus VI over delta T. So then work would be equal to VF minus VI over delta T times delta D. But delta D over delta T, this is really just VAV, right? Delta D over delta T is equal to V average. So work then is equal to VF minus VI. Oh, I lost the M. Sorry about that. M. Times V average. But what is your average? Well, you can find the average of anything by adding the two quantities up and dividing by 2. So work then is equal to M, VF minus VI, times VI plus VF divided by 2. If I pull the 2 out in front, we would have 1/2 M. And now to multiply these together, I have to FOIL them. So VF times VI will be VF VI. VF times VF will be VF squared. VI times negative VI times VI will be negative VI squared. And negative VI times VF, negative VI VF. Hopefully, if you look, you'll see VF VI and VI VF, negative VI VF will cancel. So we're left with W is equal to 1/2 M VF squared minus VI squared. If I multiply this through, I get W is equal to 1/2 M VF squared minus 1/2 M VI squared. What is this really? Well, this is the final kinetic energy, and this is the initial kinetic energy. So what we have just proven is that work done is equal to the change in kinetic energy. Okay? So we will use this a fair bit when we're doing work that causes an object to speed up, and you will use it tonight in some of your homework questions. Okay? I want to talk about a second type of energy now, that's kinetic, and I've already mentioned this one as well in class. Okay? It's under the category, it's a mechanical still, but we've talked about potential energy. And potential energy is energy that is stored in the system. Okay, so there's all different types of potential energy. And they're all energy that's stored. And the test to see if something has potential energy is to release it. And when you release it, if it moves, it has potential energy. Okay, so if it moves, it has potential energy. For example, I take somebody to the roof of the building and I hold them off out over the edge, and you say, hey, does that person have any potential energy? And so as I ponder and rub my face, I let go, and the person immediately begins to fall. And it's like, oh yeah, look at that, they did. Because when I released them, they moved. The type of energy that they would have there would be known as gravitational potential energy. Okay? And if we think of work done is equal to F delta D cos theta, to get that person to the roof, I would have to apply a force equal to their weight. And their distance that they traveled would be their change in height. Okay, and so I've carried them up. Force is going up, delta D is going up, so theta will be 0. And so work done will equal M HF minus HI, so we're mg.